what spring is like on Jupiter or Mars. In other words, take my hand. In other words, darling, kiss me. And that was Fly Me to the Moon by Frank Sinatra. Happy Halloween, everyone. I continue here. And that was Finian's Rainbow. one is Explorer. I just left that one out. I'm going to try Kim Robertson in a bit. I'm just working on something called Moving Cloud. I know it's been rather warm, but I wanted to celebrate that we had a little bit of rain about a few days ago. So here we go. This is Moving Cloud. Am I out of time? Oh, I'm.
You need to.
Oh, well, happy Halloween, everyone.
Happy Halloween. And thank you again so much. And happy Halloween, everybody, and welcome to the October meeting of Orange County Astronomers. As is not unusual, we are having a few technical glitches, but here we are ready to go. And we have a great program. We have a speaker. Actually, what's really great for us in the hall is both the speaker and our What's Up person are both here too, in person. So that is a reason why all of you should think about coming here too one of these days. Now, we have a number of regular people who are usually here, but are at Nightfall. I was thinking star something. Nightfall, which is one of the last regional astronomy things that is still going on. It's our last remnant of RTMC, for those that remember back to those days. And if any of those are online, I hope y'all are having a really great time. We miss you, but we'll be looking forward to hearing about it. I suppose I really ought to introduce myself, just possibly. People don't know who I am. I am your current president, believe it or not. My name is Barbara Toy, and we actually do have an election going on. If any of you are interested in running for an office for the board for next year, get your nomination in to Alan, who is here. It's it's Alan at astronomers.org is the address. The nominations, as we have, I'm sure, told you far too many times, but anyway, they end at the next meeting. And the November meeting is going to be, as another reminder, a week earlier than our usual date. So please remember to come the first Friday of November to the in-person meeting. And without more ado, I think it's time to turn this over to our
Mark Price. Mark Price.
Oh, that's right. I apologize. Mark, are you here? We also tonight here on the ground have the one of our special interest groups that is attending the general meeting because this is their usual night. Mark over here, and he wanted to sort of introduce the group and briefly and let you know what you're missing if you don't attend their meeting.
Thank you. I'm Mark Price, for those of you who don't know me, which is probably most of you, and Steve Schultz, who and I'm the current coordinator of the Astrophysics Special Interest Group. Steve's the rising coordinator. And it could describe us as a cohort of STEM interested members of Orange County Astronomers. And current activities, we have speakers, we do tours. We've been to JPL, been to Mount Wilson, been to where else? Goldstone, and actually a group of us went out to see the fusion experiment at General Atomics. So we get around, we travel, we don't just sit in the conference room. And we meet at Orange Coast College on the third Friday of the month, usually. Anyway, he needs to start getting practice, so I'm going to turn it over to him from here.
Thank you. Again, my name's Steve Schultz. I've been part of the Astronomy Club for a little over a year. but I really appreciate the group that I found with the ASIG, and circumstances are that I'm going to work into it slowly and making that transition happen. But I kind of feel like that and want to continue with what Mark has set up. This is really a thriving group of folks that are really interested in astrophysics topics, both current and really understanding what's going on, but also learning. So, we had a long running course on, different techniques in astrophysics. But really, it's not just for, academics. It's really for stargazers like me and citizen scientists or anyone who's just curious. So I'm hoping that we can continue along with that. And in terms of goals, I'm thinking, let's just keep it fun. We all enjoy each other's company. So I think that's a good thing to keep going. We definitely have engaging and interesting things we talk about. And Mark described all the field trips we've taken. I think we want to continue that. And, really just continue to discover and learn things about astrophysics. So, that's my vision. I'm hoping that we can continue on.
How many of our attendees are here tonight? So I want to make those of you who don't attend jealous that you haven't joined us yet. And so it's, we do have a pretty good time. And one thing we're pondering, I'll mention, is possibly doing some research projects. You'd be amazed with what you can do with stuff astronomers have around their homes. And you think about it, that's all there was until maybe a century ago, and a lot of progress was made. So that's another possibility for upcoming activities. And anything else?
Perhaps some of the things we can do is visit other groups, like go visit some universities and talk about what they're doing and maybe do some things with them. So I think that would be a great thing. I know there's a big program over, I think it's Pomona College. They have some deal where they can use some of the, there's an observatory up at Table Mountain. I guess they are able to use some of the facilities up there. So, and they're doing some great things over just with the classes at the university. So, things like that. Maybe a little bit of outreach, work with some of the other groups here in our club. So, yeah.
Bottom line is, if you're at all interested in astrophysics, that's the group to go hang out with or join up with. Well, thank you both very much.
Thank you.
Yeah. And now I think it's time for the club announcements. Turn it over.
Kyle's not there. I don't have them downloaded, Raising.
Okay, let me go ahead over them then. Shall I?
If you just play him, we can talk over it.
Yeah, you.
Oh, okay, sure, I have it. Go ahead, Barbara.
Okay, can we control them from here? Or are you going to roll them through?
I will roll them. So you just tell me next slide.
Okay. Again, welcome. As you may notice from the slide, which I hope is being projected up there.
Yes, it is.
Okay. And next slide. We have some new members. We'd like to really welcome them. Darren Diamond, Risai Goldsmith, Michael Kelly, and Keith McCoy. Are any of you guys here tonight? I guess not at the meeting. For new members in general, it may take a couple of meetings, but there will ultimately be a membership badge over on the whiteboard that is in front of the meeting room, and you can pick up your badge when you are next at a meeting, or Charlie will eventually send it to you, or you can request it that way. Next slide. Usually we have coffee and donuts upstairs. Thanks to Charlie, we have some donuts and some, I'm afraid, rather cool coffee, but enjoy it if there's any left. And next month, I think Helen is going to be back. And thank you very much, Charlie, for thinking to bring the donuts. That definitely can be an upper for the evening. Next slide. Star parties. We have the ANZA Star Party this weekend. It's actually tomorrow night. And the Orange County Star Parties we're still working on. We are hoping that we will have them underway in the not too distant future. Stay tuned and we will try to keep you advised. The Astrophysics SIG, which we were just told about, would normally be meeting tonight. They will be meeting the third Friday of November will be their next meeting. And Astro Imaging is November 14th. That's their next meeting. The beginners class is November 7th. And the next OCA board meeting, which is always a thrilling experience, believe me, is November 9th at 10:30 a.m. And if you are at all interested in attending, and every club member is welcome to attend, please contact Alan Smallbone, and he can send you the link. Next slide. Well, upcoming events. We have the Mount Wilson Observatory's Arts at the Observatory, presenting the James Griffith Small Paintings of Infinity. Anyway, it's an exhibit, and for those of you that are interested, there is a website link down there if you copy fast, or I think you could probably pretty quickly do a Google search for that. Anyway, it should be a lot of fun. Next slide. Dr. Brian Hart, who some of you may remember as a past member, and who has spoken to us a couple of times, he's notified us he is working toward making you may recall he has been working on a movie, and he is progressing on that, and is has some modifications. He just wanted to let us know that that is still in progress, and he thinks it is advancing well, and we're always glad to hear from him. Next slide. The Adopt a Scope program is alive and well, and there is a great stock of telescopes. We try to keep the list updated on the website. So if you are at all interested in a telescope that may have had some prior use, that's usually the case. Anyway, you can adopt it, and there's different scopes. There are different charges depending. All the details are on the website. Next slide. Outreach events. Martin Christiansen is our current outreach coordinator and is doing a great job. And Martin, I saw you had your hand up.
Yeah, just to point out the major advocacy behind that.
Great.
And also, we have 5 volunteers for next Friday's outreach at Silver Middle School.
And I'm sorry, which school?
5 volunteers for next Friday's outreach at Silver Middle School. And there's a number that does your name on it.
Great.
I started calling up volunteers for our next outreach on
November 4th. Yeah. Martin was just wanting to remind everybody who is here that hasn't had contact with the outreach program recently. He's here. He's willing to talk to you. He's always, volunteers are always needed for that, and it's a great program. He has 5 volunteers for the upcoming outreach next week, and is looking for volunteers for the next one, which, I'm sorry, that was November.
That's November 6th up there, but we had to cancel that.
Oh, okay. The November 6th one it was canceled. It's November 2nd? 14th. November 14th will be the next one. Okay. If you have any questions about outreach, definitely get in touch with Martin. Next slide. The series astronomer editor is Dave Fisher, who has been doing a great job with the transition to the all electronic version. If you have articles or items that you think would be of interest in the newsletter, please get in touch with him. content, of course, is always a concern. And right now, when we have the electronic version, and we have a little bit more flexibility with what we can do with it, and it's kind of interesting to see where that's going to take us. The next slide. Yes, a friendly reminder for those that use the ANSA site. Please remember that the last person out needs to check to be sure that everything is locked up, and close the gate. ANSA House in particular, it's important that we keep that locked, and make sure that the gate is latched at least so it doesn't swing open accidentally. I imagine well, tomorrow night is the ANSA Star Party, so hopefully a number of you will be going out there. We're hoping that the conditions will be really good this week. I'm sorry?
Fine. I'm there from the Coon Telescope.
Okay. So one way or another, the observatory should be open, and Liam Kennedy is planning to be there, whether or not I'm able to make it.
Okay.
Thanks, Liam.
Yeah, no problem.
Okay. Next slide. Yes. You may recall we had this big weed clearance and brush clearance and so on project at ANSA to help us with our fire protection efforts. Since then, we've had a number of thunderstorms and so on. It always happens over the summer and the monsoon season. We've had some weeds come back. So it is something we need to do on a regular basis. We need to make sure that we're keeping the weed growth under control so we don't lose the benefit we got from the effort made to do the clearance earlier this year. That would also include the new fire protection, I won't say roads, but they're clearance areas that run along the borders of the site. The fire breaks. Thank you. So yeah, if you can, when you're next out there, spend some time helping to clear those areas out, that would be of great assistance to all of us. Next slide. Yeah, I mentioned the elections earlier. This is the slide on it. I've talked about it a couple of times in the president's message, trying to give people background. All of the offices, that's the 4 officers, president, vice president, secretary, and treasurer, and the 7 trustees at large. All of those positions are up each year. If you run and are elected, it is only a 1-year commitment, if that makes you feel better about it. Even though some of us enjoy it enough that we actually stay on much longer than that. And actually our board, I'm happy to say, has been working together very well. Actually, Liam Kennedy, who I mentioned before, he is our newest trustee. We had someone who had to leave, and so he stepped in. Well, someone is Doug, actually, who usually would be here, but he's down doing nightfall. Anyway, so it is a lot of fun. It's helpful to the club. It's great to have people with a variety of viewpoints and backgrounds on the board. So even if you feel kind of diffident maybe about what you might be able to bring to it, do think seriously about running. It's important that we have new membership come on regularly. That helps keep fresh blood going, and you don't want people to become too entrenched. And one of these days, I'm going to get somebody else to run for president. Okay. And again, deadline for running, for letting us know that you want to run is the next meeting. So that'll be the first Friday in November. And again, notify Alan if you want to be on the ballot. Next slide. Raise up. Great. And see, there you are. Next meeting is November 7th, 2025, first Friday of the month. Again, I can't emphasize that enough because we do want people to show up on the right week. If you show up on the second Friday of the month. There will be something going on here. I don't know what, but it'll be a Chapman event, not ours. Anyway, with that, I will turn it over to, well, actually, next up is Chris Butler. I was going to say I should turn it over to Reza for the introduction, but since Chris is here, I am going to take advantage of the opportunity. We all know about Chris Butler. Chris has been a member for a long time.
41 years.
Wow. For those online, that's 41 years, believe it or not, and he still looks youthful. That's the amazing thing. He's an artist. He gives great presentations. He's knowledgeable in a wide array of areas, including, I believe, from looking at your website one time, dinosaurs.
Yeah, that's probably, well, so not.
Probably not, but I don't know. I understand that Earth 2 is on the agenda. Maybe there are dinosaurs there. What the heck? Anyway, without more ado, please welcome Chris Butler to do the what's up for this.
All right, fantastic. All right, I'm on camera. Good. Everybody can see me.
Just wait a second. Wait,
Oh.
let me bring up the.
I'm waiting. Kind of get the stage fright. First 41 years is the hard part. Okay. I do want to say, for the benefit of our many friends who are at nightfall and didn't come tonight, I'd like to thank the members of the Temecula Valley Nudist Skydiving Association. Thank you for joining us. Nice having you drop in. Okay, with all this being said, then let's get started with the what's up. Let's take a quick look around the sky. What is going on? Well, first of all, I don't know if you've noticed this, but I certainly have. I actually notice it more and more every year. I find actually the change of the seasons. Not only are we having the cooler weather, did you notice that it was like 2 weeks ago, suddenly we had our first cool evening. And for me, when the weather changes like that, that means I have to start setting up my Halloween display. So there's some pressure. But also, the behavior of the sun in the sky is really dramatic this time of year, because for us in the Northern Hemisphere, I will point out, the sun is dropping very quickly. This is the time of year where it changes the most over a short period of time. And the seasons really are changing. You may have noticed that the nights are really genuinely getting longer, and indeed they are. As far as phases of the moon, we are going to have the month started off with a full moon in the first week of the month. Did I do? All right. Yeah. Sorry, I got the handheld control here. Right now, though, we've swung around the half-lit moon in the morning sky. October 13th was last quarter. It's swinging around now to a thin crescent in the morning sky, and will be a new moon, dark of the moon, October 21st. That's important this month because the Orionid meteor shower is going to peak that night. So we will have dark conditions. We kind of have a love-hate relationship with the sky. If you notice this, from sucker hole clouds, comets that fizzle and don't give us what we expect, and they get surprises, things that you weren't expecting. The sky it's appropriate for this time of year. The sky's kind of like a trickster god, but maybe you'll get the show you're expecting. Maybe you'll really get surprised. And here we've got a meteor shower, and for once, it's going to be dark of the moon. But all of you have that healthy, skeptical look on your faces. You never know. Maybe that will be the overcast night. Maybe the first night in 100 years that the Orionids disappoint us. Or maybe we'll just get one really big Orionid, city-sized, that comes. You never know with the sky, right? But October 21st, good time to look for meteors. October 29th will be first quarter moon in the evening sky, half lit. That's very nice because it means a couple days later we have got Halloween. Halloween will have a very nice waxing gibbous moon for you. All right. Now looking at the planets, just running down through them, people have asked me for years, how do I remember all these facts to give in a presentation, I just put all the facts on the slide and then I read them. That's the way to cheat. And this is an example of that sort of slide. Now, Mercury is in the evening sky. You can see it after sunset theoretically, but now our speaker, of course, from Australia, this is a rant of a poor Northern Hemisphere person, because it happened to us again. The trickster sky has pulled this. We've got Mercury is swung out. It's at elongation, approximately. You can see it pretty well theoretically, except that it's leaned way over to the horizon and is beautifully placed for observers in the Southern Hemisphere. I don't know what it is. They are simply blessed by all these amazing sights. This time, if you were down south, you could see a lot better. Venus is in the morning sky, so expect to see that when you are looking through slitted eyes and you're drinking your coffee in the morning. Mars is down near Mercury in the sky, of course, back behind it. It's quite close to the sun. It's not well placed for observation right now. Jupiter is a later object. It's in Gemini. It's basically a third twin in the Gemini constellation. Very bright. Coming up about midnight, it won't be at its highest until dawn, but in the wee hours of the morning, good thing to do. Saturn is well placed right now. It's going to be at its highest or transiting around about 11 p.m. It's in Pisces the Fishes, charts to follow in a moment. One thing to note, the rings are very thin. So there's another surprise for you from the spooky October sky. If you look at Saturn, first glimpse anyway, you might think the rings have been stolen. They're not stolen. They have, however, been canceled during the government shutdown. Eventually they will be back. I'm just teasing, of course. Uranus is a morning object as well in Taurus, not too far from the Pleiades, a bit south of the Pleiades. Neptune is in the sky quite close to Saturn. If you haven't seen Neptune through your telescope for Saturn, you'll be poking around there anyway. Good excuse, just jump over and have a look. Pluto, not especially well placed. It is up in the evening sky, but it's already on its way down as the sky darkens. Oh, speaking of darkens, yeah, I guess, can you see the screen all right? Is it? Yeah. Okay, because I wasn't sure if it's not dark enough for you. They mentioned the Orion meteor shower, pieces of Comet Halley, and they are likely going to be the only bright part of Comet Halley any of us have ever seen. I'm just remembering 1986. It wasn't exactly blazingly bright this time, but it visits us again and again through some of the debris shed from that comet, and we'll be seeing some meteors at the middle of this month. The thing that is in the news, the thing you've heard about everywhere, I have to mention, because up at Griffith Observatory, every single visitor seems to know about this comet. They do know some pieces of information that are not correct, such as that it is composed of a fleet of Imperial Star Destroyers and other such tidbits, which are not true. It is an interstellar comet that makes it very interesting, drifting through our solar system, passing relatively near Mars right now. However, it is not very bright, and it is spectacularly badly placed for us. O indicates where the sun is, and X indicates where the comet is as of right now. That direction will be burning your eyes out if you try to look with a telescope. It really isn't going to be well placed during this pass, and it isn't going to be making another pass, is it? It's on its way straight out into the dark. But we're finding more of these objects now. Who knows? Maybe the next one that comes through will be close to us and spectacular and have a fleet of Star Destroyers. We'll see what happens. There are, however, some other comets. For those who like comets, Comet Lemon is visible in the morning sky, and it has a wonderful lemony fresh scent. I'm just teasing. Of course, that's named for a discoverer of the comet, but I'll show you where it is in the charts that follow. Comet Swan is also visible right now. Both Comet Lemon and Comet Swan are very dim naked eye objects down around magnitude 6. So you do need a telescope to really notice them. Comet Swan is not in the morning sky like Lemmet is. Swan is in the evening sky, just a little bit after sunset. We'll show you where in a second. This is the sky at the time of sunset. The sky would actually be too bright to look at this time, but I've shown you where things are. So you can see where Mars is, beautifully placed, exactly about to disappear at the moment the sun drops below the horizon. Almost impossible to catch Mars, and Mercury is even lower than that because of the angle of the ecliptic, the planet's path to the horizon. Pluto is well placed, but as you can see, it's at the highest it will get. It's going to slide down, and you'll see in a moment once the sky gets dark. Saturn and Neptune are already on their way up at sunset. If we let the sky go ahead and get dark, 9 o'clock, it is actually dark at this hour, and you've got Comet Swan in the southwest. You could hunt for it. It is basically between Sagittarius and Ophiuchus, if you want to know where it is. And again, about 6th magnitude. Pluto's already on its way down. Neptune and Saturn rising higher and well placed at 9 for getting a look at. And Uranus has just risen there in the east. And yes, I still really want to rename that planet to, frankly, almost anything because we have children at the observatory and the giggles are getting old. Looking at constellations at this time of night, I will mention 3 very quickly and an object or 2 in each. Pegasus is one of my absolute favorites, and it is beautifully placed at 9 p.m. during casual observation hours. In ancient times in this club, we mentioned how long I've been doing this, I would have told you that the great square of Pegasus looks like a television set. And then if you see Andromeda right next to it, up and to the left, kind of as a V shape. We'll actually talk about Andromeda in a moment. I would describe that as the rabbit ear antennas on a television. And then the curving neck and nose of Pegasus, which goes down to the star Enif, that's the power cord for the TV. I had it all worked out. It was a great scheme. I even did artwork of it. No one today living knows what rabbit ear antennas even are anymore. So if anyone has an analogy for this, great, let me know. If not, it's a big square shape, okay? Because it certainly does not look like a horse, right? It is an upside down, wingless, legless, flying horse. So it's a square with a little squiggly off the end of it. However, I am going to point out something that's easy to find. And Helen Mahoney, if you're out there at nightfall, first of all, where are you guys? Seriously. We got the hot tub fired up. And where are you? Right? Yeah, save a Merlot for me. But there's an object that she knows that I refer to as the boogers, which is right off the nose of the horse, which is on the chart there marked as M15. Right? One of my absolute favorites, globular cluster M15. This is yet another example of something that surprised us with an impossibility that is true. When I was a kid growing up, I had always learned that globular star clusters, stars, probably did not have planets because they were very ancient, poor in metals, and probably couldn't form planets. If anyone ever found a planet around another star, right? Well, lo and behold, M15 is a globular cluster, beautiful object, and one of its stars does indeed seem to have a planet. So that's an example of this beautiful object giving us a surprise. Andromeda is one of the constellations. It's immediately next door to Pegasus. One of the square stars of Pegasus is actually the alpha star of Andromeda. And we have a problem with Andromeda, especially when you've been doing these talks this long, is it's so famous and there's one particular object in it, right, that I have to cover, even though I really don't want to cover it. So sure, the big giant red blob there, the great Andromeda galaxy, of course, we're going to show a picture of that. But for the next one, I'm going to totally fool you and show you something else in Andromeda that is not the Andromeda galaxy. Yeah, I know, you're amazed, right? And what's more, I'm not going to show you, I have to lean in and double check myself, NGC 62, the blue snowball planetary nebula off in there. I'm not going to show that one either. I'm not going to show that one. I got something else entirely. Yeah, there are other things out there. But just to keep things fresh, not a recent picture of Andromeda, but instead a historical one shot up at Mount Wilson. This is a picture taken by Edmund Halley. Oh, no, Edwin Hubble. So he would have loved that. He was kind of full of himself, from what I understand. Edwin Hubble in 1923, when he was hunting, had got the big surprise of finding the Cepheid variables and proving the distance to this and finding out it was an external galaxy. So the M31, yes, it's up there, visible, even binoculars. You see it in telescopes, of course. However, the multiple star Almach, noted double star. It's beautiful color contrast. One of those ones in gold with a blue companion. However, even though I remember it as being a double star from early books and looks through a telescope, it actually is a quadruple. And Damian Peach is one of the people who has been able to split the blue companion with. Is there anything he can't do? I mean, Damian Peach is an amazing astro imager. He shoots things that really only professional observatories should be doing. And as you can see there, his images are so sharp. He's got this companion actually split. Don't expect to see that through your telescope, unless, like me, you just lie and say you can see it. Neptune and Saturn are both in the zodiacal constellation of Pisces the Fishes, the 12 constellations that anyone at a bar will know. So that's nice. You can say, oh, Pisces the Fishes, because Saturn's naked eye bright. The stars of Pisces, however, of course, they're not very bright. But if you want, with a pair of binoculars, to say you've seen Pisces, some people in the city especially, you might not have noticed it, go and look at Saturn and then just pan slightly up, and you will find a circlet of Pisces that marks the position on one of the two fishes that Pisces represents. They are connected by a cord or a string. That's the big V shape. And then at the other end of the constellation, those are supposed to be fish, another fish. So anyway, that's where those two planets are in this constellation. For an object to look at, M74 is a good example of a face-on spiral galaxy. It is also a lesson in how dim most galaxies really are if you're looking from the city. And they do have this, appropriate for this time of year, ghostly kind of soft glow appearance like you see here. And for a weird one, I'll throw in NGC 520. This is partly for my friends in the cosmic debris who are down there at nightfall. Because they like the exotic objects, the strange objects. I think it's pretty safe. I have never featured the collisional galaxy system NGC 520 before, but if you're down there at nightfall, you've stood us up, you're missing out on the hot tub and the Merlot and the skydiving. If you're down there, hey, you may as well do something with your night. So get out there and find NGC 520 for all of us. Come back here and tell us what it really looks like. Getting out to midnight here, you can see the planets have swung around some more as the sky rotates. Note the presence of dwarf planet Ceres down there. As anyone from Los Angeles knows, we are going to the World Series. I'm sure we must be, the way things are going. So here is actually not a full planet, but it is a World Series. Just saying. All right. What did you pay to get in here? At this hour, Jupiter has risen, and if you are looking at Saturn there, this is a recent picture to show how edge-on the rings are. And then you let things get around out towards sunrise. You've wasted another night of your lives out there at nightfall when you could have been here. And you'll see a sliver of a moon. Venus will be rising as well. And that's a pretty fun packed evening as we start getting ready for Halloween. With that, I will leave you for all that fun. And thank you again for your time and attention.
Thank you very much, Chris. Alan?
You haven't shared your screen yet. There we go. This is the same as the screen. This is the same as the screen.
Brilliant. Okay, but I need to stand here.
You just need to stand right here in front of your computer.
Okay. And the folks online can hear?
Yes, you're good. Can you hear us?
Yes.
And shall I do a quick introduction?
Sure. Very quick.
So our speaker tonight is the chief scientist of the NASA Exoplanet Science Institute and a TED Fellow. She has worked on NASA's Kepler, K2, and TESS missions, searching the sky for exoplanets, and is helping plan for NASA's next big flagship missions, the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory. Please join me in welcoming Dr. Jessie Christiansen. Jessie.
Hi, everybody. Thank you so much for coming out. I know it's not a regular night, but I'm really pleased to see everyone. I will probably rush a little bit because I only have the babysitter till 10 o'clock. So I'm going to go. It's going to be great. We're going to talk planets. It's going to be a lot of fun. Okay. So you guys probably know what this is. Not to scale, more lens flare than a J.J. Abrams film. It's the solar system, poorly rated, only 1 star. 8 planets. I know. Chris even put Pluto on his slide. 8 planets. If you ever feel bad about Pluto being demoted, don't worry. Pluto went from being the worst planet to the best dwarf planet. It totally got its whole own type of object that it gets to be the best of. So Pluto is doing fine. So we also have a bunch of dwarf planets in our solar system. We have minor planets in our solar system, which is everything else we've been able to catalog, bigger than a grain of dust. There's over 1 million things we've found just in our solar system. But what are exoplanets? Exoplanets are planets around other stars. Our star is just one of the thousands we can see in the sky and the hundreds of billions we know are in our galaxy. Exoplanet is an idea we've had for a long time about other stars. Okay. So I talked a little bit with Chris before we started about the fact that the southern sky is better than the northern sky. And I hope you all get to appreciate that someday and get down to Australia to see it. That's where I'm from, if you can't tell. Can you guys all see the emu in the sky? Have a look for a second. And then I'm going to put a very terrible cartoon that I drew on top. See? So the oldest oral tradition we have on Earth is the Indigenous Australians and their stories about the sky. Their cosmology, the dreaming, is set in the sky. And they tell stories in the sky, not with the stars, but with the dust lanes, right? The emu is the dust. It's not stars, it's the dust. And I think there's something incredibly poignant about the fact that the oldest stories we've been telling ourselves are stories about what the sky can tell us about where we come from and where we're going. So literally for tens of thousands of years, the oldest stories we have are stories about the sky. Okay, but let's narrow back down on exoplanets, specifically this idea of exoplanets around other stars. These are the Greek philosophers, so we're talking 2,500 years ago, and they're having this conversation about the idea of other Earths. Is Earth singular or plural? Now, for the Greek philosophers, this is well before the invention of the telescope, this is a thought experiment, right? They did this. They sat around, they thought big thoughts, and they're thinking about the idea of Earths. So Plato and Aristotle actually argued that Earth was singular and that there were no other Earths. Okay, let's jump forward. Now this is about 1000 AD, and this is an Iranian mathematician. And he comes along and he's like, I think there's 1,000 worlds out there, some of which are like Earth and some of which are different. He's like, yep, Earths are good. I think there's Earths out there. Let's jump forward to 1600. Now we're in the Renaissance. This is an explosion of art and math and science in the Western world. This is an Italian mathematician now, Giordano Bruno. And he says, I think there are countless planets all orbiting their stars in the same way as our planets. And it turns out that 1600 was a rough time to be in Italy and claiming that there might be other planets. He was actually burned at the stake by the church because this was heresy. He also said a bunch of other stupid stuff about the church at a time when the church had a lot of power. But one of the things he was burned at the stake for was claiming that there were other planets, other Earths. So thankfully, as an exoplanet astronomer, nowadays, I don't have to worry quite so much, although the government is shut down right now. So I'm glad I could be here. In my personal private capacity as a citizen. So he's like, yes, there are planets. And then he hits on the problem, right? There's a reason we've been thinking about it for thousands of years and hadn't found them. Stars are really, really bright and planets are really, really faint. So Giordano Bruno is like, I think they're out there, but I just think we'll never find them. It's too hard. And now let's skip to 1952. This is Russian-American astronomer Otto Struve, and he has this paper. It's 1.5 pages. I'm gonna show you a little bit of it, where he's like, yeah, we can find them. We just need to build better instruments. It's fine. And so he has this idea. So you're an amateur astronomy club. I'm sure you know about eclipsing binaries. So stars that are orbiting each other and they regularly block each other's light. They're lined up just right. And we can see those two ways. One is with their light. They block each other's light. So if you're measuring the light with time, you see dips in the light. And the other way we see them is with their velocity. If we take a spectrum of the light, we can see sometimes the light is moving towards us as the star is moving towards us, and sometimes the light is moving away. The wavelengths of the lights get stretched and they get squished and stretched. And he's like, look, if you took one of those stars out and put a planet there, a big planet like Jupiter, really close, we could see that. We just have to get better instruments. And the whole rest of the astronomy world was like, Otto, you're crazy. Sit down. Because we knew where giant planets were. They were far away from the star. Jupiter and Saturn are many, many, many astronomical units, the distance between the Earth and the Sun, away from our star. So there's no chance you could have a giant like Jupiter right next to the star. So you could see this. So between 1952 and 1995, about 40 years, this paper has 7 citations. So citations are the currency of science. So when we publish papers, the way you recognize how big an impact that paper's had, how many people it's reached, how many people think your idea is interesting, is the citations. How many times does it get cited by other scientists? So I'm here to tell you 7 is not a lot in 40 years. So he is like, there are planets and I think we can find them. And everyone went, nah, don't think so. Okay. What happened in 1995 that was incredibly exciting, actually it was 30 years ago last week, was the announcement of a first Jupiter-like planet around a sun-like star, 51 Pegasus b. This is the Nature paper. So speaking of the currency of science, if you have a paper in Nature, that's very exciting, sometimes wrong, but very exciting. And this is it. This is the exact type of planet that Otto Struve had predicted. It's a giant planet that orbits the star in 4 days. So Mercury, which is the closest planet in our solar system, right, has a period of like 88 days. 4 days. This is a Jupiter-sized planet on top of the star. And they found it using this velocity technique. They built a spectrograph that was precise enough to be able to measure this. This is incredible. This is thousands of years of thinking about this idea of planets around other stars, and we've done it. This is the front page of the New York Times 30 years ago last week. It's not It's not a digital copy, it's a scanned in copy. So we're talking about the price of the subway. We're talking about how Medicare is too expensive. We're not really talking where there's nothing. There's nothing on the front page of the New York Times. I had to go to page A29, which is literally where the classifieds start, to find the article in the New York Times the day the first planet was announced around a star like the sun. 2 sightings of a planet orbiting a sun-like star challenge the notion that the Earth is unique. And then there's a little subheading that says, is there life elsewhere in the universe? We have to ask that question now. We know that there are planets around other stars. Is there life elsewhere in the universe? That's why I'm here. Because this 30 years ago is the most exciting question that I think we can answer. And we're finding ways to answer it. And I'm really, really excited about that. These are the 2 Swiss astronomers, Didier Queloz and Michel Mayor, who made this discovery. And in 2019, they were awarded the Nobel Prize in Physics for this discovery. Okay, let's keep going. Now you can all see the emu. This is an animation that NASA had commissioned a few years ago showing where the planets are that we found. Now, because of the technical snafu, you're not going to hear it, but it's playing a note every time a planet gets found. So on the sky, you're seeing where the planets are being found and the different colors of the different ways we've found them. So those 2 different ways that Otto Struve predicted are the 2 most productive ways we have of finding planets. Still today, they're the 2 most successful techniques. And you can start to see as the years tick up, things start to really get exciting. In 2009, which is when Kepler launches, this is the Kepler field here. You're going to start to see, yep. Eventually, Kepler's not able to keep pointing there, and it starts doing an ecliptic plane survey. So you'll see this kind of sine curve appear. You'll see the microlensing planets towards the center of the galaxy that we found. And then in 2022, 3 years ago, we hit 5,000 planets. And then just 1 month ago, September 17th, we hit 6,000 planets. So we've gone from nothing for thousands of years to thousands of planets in just decades. It's such an exciting time. Okay, so what are the kinds of things we found so far? 30%, so 3 out of every 10, are gas giants, like Jupiter and Saturn. Now, many of them are very close to their star, so they're not like the Jupiter and Saturn of our solar system, but 30% of them are gas giants. Now, interestingly, we don't actually think that 30% of all planets are gas giants. It's a bias. These are the easiest to find. So, of course, they're the ones we find the most of, right? So we think that it's more like 5 to 10% of planets are gas giants. And we do actually think that cool gas giants are more common than hot gas giants. But again, we just have this bias where it's much easier to find the hot ones. So we find all of the ones that there are. Okay, let's go down to this corner. 35%, so just over a third, are like the ice giants of our solar system, like Uranus and Neptune. Again, most of the ones we found are warmer than our ice giants, which are many tens of AU away now from the sun. So we think they probably formed differently from our ice giants, and we're still thinking a lot about what their composition is, what they're made of, and how that compares to our ice giants. And we still think there's a bias there. We don't actually think that a third of real planets are this big. It's a detection bias because they're giants. Down in this corner, so 31% of planets are what we call super Earths. So in our solar system, we have the rocky inner planets and then the giants, the ice giants and the gas giants, right? And there's actually quite a big size separation between those 2 classes of planets, small planets, big planets. There's not actually a lot in the middle. And in fact, the most common kind of planet we found when you correct for these biases is a super Earth. It's something we don't have in our solar system, bigger than the Earth, smaller than Neptune. So we don't actually know what they are. We don't know whether they're just big rocks, right? If you took an Earth and scaled it up. We don't know whether they're mini Neptunes, if you took an ice giant and scaled it down. We don't know if it's a type of planet we just don't have an example of in our solar system, like a water world. In fact, the very first one we found is nicknamed Kevin, after Kevin Costner from World. We don't know. It's difficult. We really only get the bulk properties of most of these planets, so a size and a radius and a mass. So you get an average density, but that's tantalizingly not enough information to really know what it's made of. And the final quadrant, little corner up there, 4%. So 1 in 25 of the planets we found so far is a rocky planet. Now, you'll forgive me and NASA in general for a little bit of anthropomorphism. Rocky planets are where we're looking, right? Because we don't know about how life started, but we know we've only found it one place, which is on a rocky planet with liquid water. So that's our goal. We're looking for Earth 2.0, a rocky planet with liquid water on the surface. So far, we haven't found a lot. You know, this problem that Giordano Bruno really identified is that planets are really small and really hard to find. And the smallest planets are the hardest to find. And we don't want to find rocky planets right next to the star. They are cool, and I'm going to talk a little bit about them. We want to find rocky planets out here where the temperature is right for liquid water. So far, we're still looking. Which brings us to how are we doing with that search? Okay, so I mentioned the NASA Kepler mission, which I worked on for many years. This was a 1-meter optical telescope that was launched into space in 2009. So it looked at that one field of view, that 10 by 10 degree field of view in Cygnus, this one here. That's the footprint of all the CCDs on the sky. So it's easy for the people in the Northern Hemisphere to find in summer because Cygnus is right overhead and Vega is over here. So it's the footprint between Cygnus and Vega. If you look at that, we know of thousands of planets in that patch of sky, which is very cool. So Kepler used the transit method, which I'm going to show a little animation of. So this is an animation of a system called TRAPPIST-1. TRAPPIST-1 is the small, cool red star in the middle, and it has 7 rocky planets orbiting around it. Now, normally we would have no way of seeing this. They're tiny planets around a tiny star, but we're lucky, and it's lined up exactly right so that the 7 planets pass between us and the star. So now you guys are actual amateur astronomers, so I can show data and you're not afraid. This is the brightness of the star with time on the bottom, taken with the Spitzer Space Telescope. And so what you'll see is there's some noise, like the star isn't constantly bright. But what you'll see is these dips, these regular dips in the brightness that happen. Now, this one's complicated because there's 7 planets, so there's 7 different signals in the data, but you can tease them out and see these things. Now, taking the brightness of a star, like I heard mention of the astrophysics group, you guys are thinking about research projects. You can do this from the ground with like a 4-inch telescope and a CCD. You only need 1% photometry to get planets like this. You can do this. And we have a network of amateur astronomers around the world who help us confirm planets with their telescopes at home. You just need just CCD. But it's just measuring the brightness of stars, right? Which is one of the oldest types of astronomical measurements that have been made ever. It's what astronomers thousands of years were doing, measuring the brightness of stars. Okay. So let's keep going. Okay, so what have we found so far? Again, I'm showing a plot. You guys are going to stay with me here. It's going to be great. On the y-axis, the vertical axis, I'm showing this amount of, I'm showing the temperature of the star compared to the sun. So the sun is at the top and a cool star like TRAPPIST-1 is at the bottom. On the horizontal axis, I'm showing how much starlight the planet receives relative to Earth. So Earth is at 100% and the sun is at 100%. So that's the Earth. Okay, that's where the Earth is on this plot. Here's what we found so far. What you'll see is most of the planets are around smaller stars, and that's that same detection bias I mentioned before. It's easier to find things around smaller stars because the same size planet will block more light, relatively speaking. So it's easier to find things around small stars. Most of the things, these are actually, the planets are to scale with each other in terms of size. Most of the things are bigger than Earth because of this observation bias. The first thing you should take away is that there's not a lot of things right next to the Earth, right? The top half of the plot doesn't have a lot. So let's talk about what it does have. So this is Kepler 452b. And now I'm going to stop and apologize. Exoplanet names are garbage. just garbage, just rubbish. I mean, they're so bad. We had an opportunity, right? Humanity had literally been thinking of this for thousands of years, and they found one and they were like 51 Pegasus B. And it was just like, oh no, now we have to go with that naming scheme forever. So Kepler 452b is the 452nd planetary system found by the Kepler mission. B means it's the first planet in that system because the star is on. So Kepler 452b, this is as close as we got. This is orbiting a star like the sun. That's great. See, it's at the top of the plot. It's a bit big. It's about 1.6 times the size of the Earth, which is where we start to get worried that it's not just a scaled up rock, but that it's something different. It has a period of 372 days, which is pretty close to 365 days, which is pretty exciting. So all in all, put it all together, and yeah, you've got something that has maybe a 50-50 chance of being a rocky planet in the habitable zone of a sun-like star. The problem with Kepler 452b is that it might not be there. So what else has a period of 372 days is the Kepler spacecraft. So Kepler is actually orbiting the sun in an Earth trailing orbit. So as the Earth is going around the sun, Kepler's following like a little puppet. And if you've ever tried to do data analysis before, if you have a period in your instrument that appears in your data, it's not good. It's really hard to disentangle the source of that signal from the instrument, right? Because if the instrument is doing anything on a periodic thing like changing temperature, which it's doing as it goes around the sun, that's going to appear in the data. And in fact, that's what we see. If you look at the distribution of signals out of Kepler, there's a huge spike at 372 days. So either nature really likes to make planets with the exact period of the Kepler spacecraft, or they're false positives. So Kepler 452b might be a false positive, which would be a shame because it's the closest thing we have. So that's why I'm standing here today saying we haven't found Earth 2.0 yet. We have found cool planets. So let's talk about other planets on this plot. So TRAPPIST-1. So remember I said TRAPPIST-1 is very small and very cool. It's only 8% the mass of the sun, which is literally as small as you can be and still respectably call yourself a star, right? If it was 7.9% the mass, it would be a brown dwarf. It's right on the edge. But it has 7 rocky planets around it. And the middle 3 are in the habitable zone. The 2 that are too close are very hot. The 3 in the middle are just right. And then the 2 that are further out are too cold. So 3 planets in the habitable zone. Now, this is the front page of the New York Times when TRAPPIST-1 was announced. This is literally the front page of the New York Times. This is above the fold, folks, because these were rocky planets in the habitable zone. This is what we're talking about. Let's try and find these Earth-like planets. The problem with M dwarfs, these small, cool red stars, is that they put out a very different radiation profile than our sun. So life evolved around our sun for reasons we don't know. We're working on it. But M dwarfs put out a lot of high energy radiation. That's UV and X-rays. Now, I don't know if you've been to the dentist lately, but when they make you put on the lead apron at the dentist when you get an X-ray, that's because X-rays are bad. And I'm from Australia, so I'm also here just as a PSA to say UV is bad. Please wear sunscreen and hats just all the time. So we just don't know whether planets orbiting these stars could have life on them, right? We use UV to sterilize lab equipment. Like these might just be sterilized. We don't know. So that's why, front page of the New York Times, hooray, but also, maybe. So I don't know if anybody remembers Superman. He's been in the news lately. There was a whole movie. He has powers because his Krypton is a red star, and he came here to our sun, which is a yellow star. And the different light of the sun gave, I just love the fact that Superman includes actual stellar radiation profiles if you dig into it. That's amazing. Anyway, the radiation profile of the star matters. Okay, this is the last one I'll talk about on this slide. This is Proxima Centauri b. Proxima Centauri is literally the closest star to us when you leave our solar system, right? Like as soon as you leave our solar system, if you need to go borrow a cup of sugar, it's Proxima Centauri b. Proxima Centauri b has a rocky planet in the habitable zone. The very closest star to us has a rocky planet in the habitable zone that we're pretty sure is actually real, for one thing. But it is an M dwarf, right? Proxima Centauri b is an M dwarf. So it's very exciting and it's really close, but we're just not sure if these planets can be habitable. So the big question that Kepler was launched to answer and that I've spent my whole career working on is the frequency of Earth-like planets. How common are they? Kepler wasn't launched to just find one or two. Kepler was launched to answer the question, how many are there? This question that the Greek philosophers had been thinking of. Now, you might wonder how we can answer this question, given that we found no Earth-like planets. And I'm here to say scientists have never let a lack of data stop us before. So if you extrapolate, which is a very dangerous word and a very dangerous tool that scientists like to use, if you extrapolate from the parts of parameter space that we know well, which is the bigger planets at shorter periods, we think something like 10 to 50% of stars like the sun have a rocky planet in the habitable zone. Yeah, and I just want to let you sit on that for a second. That's up to half of sun-like stars, G stars, in our galaxy, of which there are billions, have a rocky planet in the habitable zone. That's a lot. That's a lot. And the number around M dwarfs is even higher. We think it's 100%. We think M dwarfs seem like they just make rocky planets all over the place. So if they're habitable, the habitable real estate in the Milky Way galaxy is incredible. And so this is a big error bar, right? That's a factor of 5 among friends, but it's because we actually don't have any and we're extrapolating. But that's very, very cool. And, you know, Reza mentioned in the introduction, the next mission that I'm working on, the Nancy Grace Roman Space Telescope, is going to help us get these error bars much smaller. And in fact, part of the reason I'm pretty tired and wired tonight is because I've just been at a 5-day meeting where we're planning out our first Science with Roman, which is going to launch next year, which is very, very amazing. You know, people have been working on this for decades and I've been working on it for years. So that's going to launch next year and is going to help us make this error bar much smaller. Okay. So I saw Steve actually had a JWST shirt on. So one of our best prospects for understanding whether rocky planets in the habitable zones of M dwarfs, these small, cool red stars, are habitable is JWST. Now, these planets are usually found by transiting. They're passing in front of the star. What that means is if they have an atmosphere, that atmosphere passes in front of the star and the starlight goes through the atmosphere. Now, atoms and molecules in the atmosphere of the planet will block light at certain wavelengths, right? Like water blocks light at 1.4 microns, which is JWST's sweet spot. So one of the things JWST is doing right now is looking at the TRAPPIST-1 planets to find out if they were able to hold on to atmospheres, given the radiation from their stars, which is incredibly exciting. Okay, so we haven't found Earth 2.0 yet, but we think that they're common. We think they're common, given how common every other kind of planet seems to be, and the fact that we have one. We infer that they're common. But we have found lots of other interesting things. So I'm just going to race through other things that we found. So hot Jupiters, which is the type of planet that was predicted by Otto Struve. There we go. Come back. Here we go. So this is an animation of a system called HD 189733b. They've just got such terrible names. So this is one of the hot Jupiters that we know best. And we've been able to study its atmospheric composition, temperature profile, and wind speed. And so one of the things we know about HD 189733b is that it's raining liquid glass sideways constantly. Like it's right next to its star. It's heated up to 2000 degrees and the atmosphere is full of silicates. So those silicates are just being blasted at 2 kilometers a second across the terminator of the planet. I did promise to say that we have found rocky planets that are very close to their star. So this is an animation. This one's actually to scale. This is how close this planet is to this star. This is Kepler 10b, which was the first rocky planet that Kepler found. And it has a period of less than 1 day. It is almost on top of its star. So what happens if you take rock and you heat it up to thousands of degrees? Liquid magma. So we think that the substellar point, this planet is definitely tidally locked to its star, the way the moon is tidally locked to us, always showing the same face. We think that the substellar point of the planet is just a magma ocean, right? It's just constantly facing the star, and that the surface is getting blasted away. This is a cloud of silicates that we're going through. And so we have found a few of these now, these lava worlds, and they're one of the most interesting types of planets that we found. All right. I've already talked a little bit about this mystery of super Earths and sub-Neptunes, so I won't go into too much detail. This is the relative sizes of planets in our solar system, and this is this gap that I was talking about between Earth and Neptune, right? So there's this huge gap here, and most of the planets we've found, both in number and we think in frequency, are in between. I think I heard you guys had Mike Brown come and talk at some point. Or maybe at Mount Wilson. Someone was telling me about Mike Brown. He's a professor at Caltech who's predicted that there is a planet 9. It's not Pluto. It's a different planet further out. If planet 9 is real, it would be a super Earth, right? Which might answer the question of why we don't have the most common kind of planet in our solar system. Seeing double, another type of planet we have found. Hopefully this is the right audience for a Star Wars reference. So this is obviously Luke Skywalker on his home world of Tatooine, this vision in the 70s. This is decades before we found any planets of this double sunset. We have actually found Tatooine-like planets with multiple stars. So this is an example of a system that has 2 stars and 3 planets. And one of the things I like is that this is George Lucas decades before we found any planets. He even got the colors right. It's like a yellow star and a red star. I mean, it's so cool. So we have actually found Tatooine-like planets. All right. So all is not lost in the search for Earth 2.0. One of the other things Reza mentioned at the top of the talk is that the next big mission that I'm working on is called Habitable Worlds Observatory. And it is what it says on the tin. We are trying to look for rocky planets in the habitable zones of sun-like stars, with enough precision that we can look for biosignatures, so signatures of life. Not even just see that the planet is there, but characterize it and be able to look for signatures of life. So this is an artist's animation of what it might look like. It would be something like a 6 to 8 meter optical infrared UV telescope with a very exquisite instrument called a coronagraph, which would block out the light from the star and let you look for planets. That's one of the techniques that we've used. I haven't talked about it yet, but direct imaging, you look for the planet. It's just really hard because of that contrast ratio. So the idea for the Habitable Worlds Observatory came out of the decadal survey. So every 10 years, all of the professional astronomers in North America get together and decide what the priorities are for the next decade in terms of what kinds of instruments, what kinds of facilities from the ground and from space. Now, these are really useful documents to take to places like NASA and NSF and be like, look, we all agreed the thing we want is insert cool thing here. And because then you can show there's consensus, right? And that, you know, people have thought very deeply about where the technology is, where the next big discovery opportunities are. And so this is a highlighted section of the 2021 decadal survey that came out, inspired by the vision of searching for signatures of life on planets outside of the solar system, and by the transformative capability such a telescope would have for a wide range of astrophysics. The survey recommends that the first mission to enter this program, which is highlighted further up as a maturation program, is a large, approximately 6 meter aperture infrared optical ultraviolet space telescope. So that is now what is called Habitable Worlds Observatory. NASA convened a START team, Science, Technology, Architecture Review team, which was 20 scientists and engineers from around North America to start defining this. I was incredibly lucky to be chosen to be one of those 20. So I've spent the last few years now working on what this telescope will look like and what it will be able to do, which is amazing. And this is an example of what it'll be able to do. So this is real data right now from the Keck telescope. So Keck is the big 10-meter telescope in Hawaii. And this is what a coronagraph can do. So the coronagraph has blocked out the light from this in the center. This is where the star is. This is everything else I showed, except for that Spitzer data, has been artists' conceptions, right? We don't actually have pictures of any of these planets. This is a real movie of 4 super Jupiters, very large, very hot planets orbiting this young star, very far away. So this is the best example we have. This is this 4 planets. You're watching 10 years worth of these planets move around this star. That's so cool. Like in astronomy, we hardly ever get to see stuff move, right? Like it's moving. We're watching the movie. Anyway, so the goal with Habitable Worlds Observatory is to be able to do that for our solar system if our solar system was 30 light years away. So if you took our solar system and put it 30 light years away and pointed HWO at it, this is what we'd want to be able to see. And the idea being that if you can isolate the light from the Earth, so we saw that cool image that Chris showed of splitting those 2 stars, that single star that's so close together into 2 stars. When you split the light apart like that, you can analyze each star separately, right? Their light isn't contaminating each other. That's what we want to do here. We want to separate the light of the Earth, of the Earth-like planet from the star so that we can take this light and then turn it into a spectrum. Heck. All right. Last plot, I promise. So this is a spectra of the Earth through time. So this is, you take the light, you split it into different wavelengths, and you look for those features of atoms and molecules that I mentioned that are absorbing at different wavelengths. Now, this is interesting. If you were an alien looking at Earth's atmosphere 4 billion years ago, it would look totally different from Earth's atmosphere today, because bacteria and amoeba have spent 4 million years oxygenating the atmosphere and creating this atmosphere that we have today. And so if you came 4 billion years ago, you'd be like carbon dioxide and methane. Oh, not great. But if you came and looked today, you'd be like, oh, water, oxygen, this is great. So the point is, we want to be able to get spectra of these planets and look for signatures of life, but also understand that they might not look exactly like modern day Earth's atmosphere, which is important. Okay, so the idea is we are searching for Earth 2.0. The punchline is Habitable Worlds Observatory is not going to launch for 20 years. This is a 2040s experiment, guys. Like we had JWST just launched, Roman is about to launch. We're going to spend the 2030s building this bad boy. And then in the 2040s, we will have Habitable Worlds Observatory. And we will find this planet that we've been thinking about for tens of thousands of years and hypothesizing about for thousands of years and building instruments to find for decades. We're going to find it. And we're going to look for signatures of life. And that is as close to searching for Earth 2.0 as we're going to get. So thank you very much, everybody, for your time. And if you're not sick of hearing me talk, the QR code is for the Caltech podcast that I host, where I talk with people who've found planets about what it was like to find a planet and how they found it and what do they think about it and what's their favorite planet. Anyway, more of me talking at the QR code. Anyway, questions? If you have questions. Chris?
At what radial distance from us would this be able to still detect habitable planets? How far up can you get before an Earth would be inside the Exoplanet?
What's the spread? Oh, yes, I repeat the question. The question is how far away, like what's the range of distances from us that this will work over? It's not very large, this window. There's 160 stars that we can do this for, where we would be sensitive to a rocky planet in the habitable zone that are the right range. I don't have the distances all in my head right now. It's between like 5 parsecs and 50 parsecs. But it's not very far, because if you get too far away, then the Earth is inside this in a working angle. So it's not a huge range. Up the back.
Observatory B, you mentioned there were 3 planets in its habitable zone. Have they been able to take a good look at those to maybe determine, well, whether there were some encouraging biosymmetry there?
Yes, so it's TRAPPIST-1 that has 3 planets in the habitable zone. Proxima b has 1 planet so far in the habitable zone. Proxima b is not a transiting planet. That one's a radial velocity planet. So it's hard to do the atmosphere study with that one. With TRAPPIST-1, there are results coming out all the time from JWST. So what they have found is that the two close planets, the ones they expected to be too hot, don't have atmospheres. And the farthest out planet, which is also one of the bigger ones, so has the biggest signal, appears to have a thick atmosphere. The most recent result on one of the habitable zone planets was ambiguous. So they didn't see a big atmosphere, but they couldn't rule out a small atmosphere. So it's just, we're pushing these instruments as far as we can to try and dig into these tiny signals. So there's two more planets to look for. It's just we're going to have to build up this signal with JWST. We're going to have to visit it again and again and try and like dig down into the signal's noise. So we don't have a good result yet, but we have hope of a good result. Sure.
Online question?
Oh, there's an online question?
Yes, there are online questions.
Sorry, tell me.
Yeah. So what are the prospects of finding an exomoon?
Ooh, so one of the things I didn't talk about is that my day job is that I'm the lead scientist of the NASA Exoplanet Archive, which is how we keep track of all of the planets that we found so far. We actually have a hidden column in the main table called exomoons. I'm ready. As soon as we find an exomoon, I'm busting this column out. It's ready to go. So far there are two candidates for exomoons in the Kepler data. They're probably more, you would think of them as maybe binary planets, like a Neptune-sized moon around a Jupiter-sized thing. Like the candidates we have are very large and very noisy, so not exciting. People aren't super excited about them yet. When Roman launches next year, one of the things it might find using a different technique called microlensing is moons. But probably only in the low dozens. But exciting, but not yet.
Thank you. One more before you go to the in-person. You mentioned about tidally locked planets. Could some of those have the other side habitable because they're protected from the X-rays and UVs in certain systems?
Yeah, so we think about this a lot with these tidally locked planets because even the further out planets around M dwarfs might be tidally locked. The challenge is you need something where the atmosphere of the planet doesn't just rain out on the cold side and you lose your atmosphere, like it just all disappears on the cold side. You need some very thick atmosphere like on Venus or something, right? Like a really thick atmosphere where it's going to redistribute the heat to the cold side so that it just keeps the atmosphere, so the atmosphere doesn't freeze out. So usually people think about the terminator of tidally locked planets. So this is the twilight, right, between the permanent night side and the permanent day side. If you have a thick enough atmosphere to redistribute the heat, the idea is that the terminator might be habitable. It's kind of fantastical, but it's fun to think about.
Okay, thank you. And there are many more, but one most important, it's about the naming. Are the namings of these planets according to the discovery order or the order they are in the distance from there?
It's the discovery order. So actually some planets are labeled out of order. So my favorite example is Tau Ceti. Tau Ceti, the planets B, C, and D were eventually refuted. So the four planets that it has left are E, F, G, and H. And the order they're in is like G, H, F, E. And it's just like, it doesn't make any sense, but it's because it's a very complicated system of signals that are all kind of like bleeding into each other. So they were very hard to disentangle and get right the first time. So yes, Tau Ceti. Interestingly, for the Star Trek fans in the audience, in the Tau Ceti, in the Star Trek universe, Tau Ceti has 4 planets. And in the real universe, Tau Ceti seems to have 4 planets. So that's just another thing they got right, like well before we even had planets.
Okay, great. And just a quick note, you mentioned Mike Brown. We have had him back in May 2006. So not many folks might remember.
Well, Chris has been here for 41 years, so he saw him. All right, up here.
With some, when you're looking, by the time like the time scale will kind of longer when you're trying to find exoplanets? Or
like how long will the survey take?
Yeah,
Yeah, okay. So it's the survey we're planning is a 5-year survey, and we're going to look at something like 100 of the 160 stars in that 5 years. We're not going to spend all of the telescope time just on those 100 stars, because apparently there are other things that people like to look at besides stars that might have planets. So about a quarter of the time is going to get spent on this survey. So a quarter of 5 years, so like just over a year of time is just going to get spent on these 100 stars. And then people will do other, people care about the galaxies and stuff. I don't know. It seems like a waste to me. I'm allowed to say this because I'm married to a galaxy formation theorist. And our whole marital dynamic is me giving him crap about how boring galaxies are. All right, there was a question in the front there. Yeah, so actually the most recent dump of candidates out of Kepler was found with machine learning. So one of the things that machine learning in astronomy is particularly good for is classification, right? Like you have a training set where humans have classified a bunch of different types of data and been like, this looks like a real planet, this looks like a false positive, this looks like a variable star. And then you show that to the machine learning algorithm. You say, here's what the humans said. And then you show it a new batch of data and you're like, what do you think? And it does this classification. So there was a couple of years ago now, but there was a paper where they found 301 new planets in Kepler data by using this machine learning algorithm. We actually use machine learning at the Exoplanet Archive for something slightly different, which is one of our jobs is to keep track of all of the planets that get published and all of their parameters. And we used to do that by there were 3 scientists. Every day, one of us would just read all the papers. But the problem is the field has grown so much in the last 20 years that there's 100 papers every day. Like just reading the abstracts of 100 papers starts to be a lot. So, but it's the same kind of problem, right? You have a classification, you have 100 papers. Here's a training set of papers that the humans thought were relevant. Read these 100 papers and tell me which ones are relevant. So now we actually have this machine learning classifier that reads the new papers every day and gives us a ranked list of all the papers from most relevant to least relevant, and saves us a lot of time. So we are using it, but in a slightly different way from confirming planets. Were there more hands? Yep.
The icy planet has atmosphere.
Which planets?
Icy planet.
Our ice giants have atmospheres. So they're volatile, rich atmospheres. So it's a lot of methane and carbon dioxide, and storms and clouds and features and stuff. And so we think that many of these planets that we're finding also have atmospheres. The hot Jupiters have incredibly huge, rich, complex, deep atmospheres. And so we use things like Hubble and JWST to look into the atmospheres and see what we can find.
There one of them that make water.
Yeah, so we found water vapor. We haven't found liquid water, unless you believe these K218 results, which I can talk about later. We haven't found liquid water, but we found water vapor. So most of the planets that we've been able to do this for are too hot for liquid water, but they have steam, right? They have steam in their atmospheres. So we have found water. You just haven't found it like in puddles yet.
Thinking that we can find some forms of light at the bottom of the ocean that some energy. With the magnets still hot in this planet, maybe we can have some sort of light.
Yeah, so I glossed over it a little bit at the start, but I was trying to hint at this with the comment about how anthropomorphic we're being. There are more types of life than we could possibly imagine, right? Like I'm not going to stand here and be like carbon-based, liquid water-based life is it. There's nothing else out there. But if you're asking NASA for $10 billion to build a telescope to look for life, you better have a really good reason to say, this is where I'm going to look for life. So that's why, Europa Clipper, which is on its way out to Europa, we think there's liquid water in Europa. And we're like, let's go look in the liquid water for life. So we're not looking for all of these other types of life that might exist. And people are thinking about it. And I hope that at some point we get to do that. But we're going to do the thing we think we know first, which is liquid water.
Yeah. Have we found any evidence of molecular oxygen on the exoplanet?
Oh, O2. Someone was actually just asking me this the other day, and I went, there's a table of all of the atoms and molecules that we found. I don't think we've found O2 yet. I just looked this up in the last few months. It has been looked for, and I think it has not been found yet.
Because that would be the strongest possible indicator of life as we know it.
Yeah, but even O2, there are non-biological ways to make it. You have to have O2 and something else like methane together to be really sure that it's something like life. All right. Thank you so much, everybody. I appreciate your time.
Thank you.
Thank you very much. What a great talk, and I hope you get on time for your 10 p.m. deadline. I would like to thank everybody for attending, especially the online audience and the in-person audience. See you all November